Hello again. This is Hudson Valley QBA. We are talking about compound interest, and this is Unit 3 or Chapter 3, the second half of Unit 3. In the first video on compound interest, we got through about number 9 on your handout. So I want to give you a second, grab your handout. You can also possibly look at PowerPoint presentations at the same time. But I would like you to take a look at the handout. This is the correct handout you should be using. It's the first one for compound interest. We got through compound interest. This is the future value, just review, of compound interest. And then we got down here to question 9. And finding the number of compounding periods. Because sometimes we're looking for future value. Sometimes we're looking for present value or proceeds with compound interest. Sometimes we're looking for the interest rate, or I, and sometimes we're looking for N. Remember, if you are giving interest or the term of the loan or the note, the first step is always to calculate I and N. So let's go over to the PowerPoints. And this is the next problem we have, 9B. Now remember, I will be going over just concepts. I might skip some of the problems in the PowerPoint presentation, but you are to go and do them yourself. So 9B, a $1,500 is in the bank for 5 years at 6.5% compounded semi-annually or twice a year. Solve for future value, discount, N and I. So the first step is to calculate N. N, the total number of periods. Since it's 5 years and we're compounding it semi-annually or twice a year, 5 times 2, there's 10 total periods that we're going to generate interest. I is the interest rate in decimal form, 0.065, divided by the number of compounding times per year. In this case, since it's semi-annually, is 2. Please try to keep this in your calculator. So here's our future value formula. And let me give you a little trick on how to do this calculation so you don't have to write down the interest on a piece of paper on the side. Start from the innermost parentheses. 0.065 divided by 2 on your calculator. Enter. Plus 1, enter, raised to the 10th power, enter, times 1,500. And you get 2,065.34. Now, discount is always the future value minus the present value. Future value minus present value, in this case, $565.34. Okay? Next. Now, this problem may be a little bit different on your handout. We don't always talk about compounding with money. We might say the number of students at a college is compounding, or it might be growing exponentially. In this case, we're talking about the number of registered Republicans grew by 6% between 1970 and 1980. There were 93,427,610 in 1970. If the same compounding growth rate continues, how many would be there in 2000? So there's a couple of things here I want to note. First of all, the period. I want you to pause this and see if you can guess what the period is. The period is 10 years. Because it defined it as between 1970 and 1980. The period was 10 years. So if we're looking at 3 decades, N is 3. Since we said 6% growth rate, and I'm not sure if that's on your handout as 6%, I is 6%. So we have our present value, 6% raised to 3. So we can predict 111 million Republicans. And this kind of emphasizes how you can be a little bit unethical reporting data. You could say, oh, so Republicans are going to be the 100% of the population by the year 2020. That is not true. That's how you can take statistics and create statistics to validate your statements. 11. What is the future value of 10,000 in an account for 3 years, 5% compounded daily, assuming bankers' rule? Okay, now this is our first problem when we are using days. And I said bankers' rule. So therefore, it's very important, N is multiplied by 365. However, I is divided by 360 because of bankers' rule. And this is just something you have to memorize. The way I remember it is, I want interest every single day of the year, or I want interest for 365 days of the year. So you have to multiply to calculate N. In this case, you multiply it by 3 years. So when you do this problem, you will end up with 11,642.45 in the bank, compounded daily for 3 years. I give you a problem here of exact interest and exact time. Pause the video and do it. Now, Section 3.4 in the book. We have different interest rates. For example, we might say 8% compounded annually, 7.75% semi-annually, 7% daily. So if we go to 3 different banks, we don't know which one's the best interest rate. So by law, they're required to give us effective annual interest rate. In other words, change all 3 of these into an annual interest rate so we can compare as the consumer. Now, when you say effective annual interest rate, it might be referred to as annual effective rate or simply effective rate. I'll let you pause this for a second and see how the effective annual interest rate formula was derived from looking at an investment of $1 compounded annually, investment of $1 compounded semi-annually, and an investment for $1 compounded quarterly. Here is the formula for effective annual interest rate. It's on your formula sheet. There's a new variable, M. M is the number of compounding periods per year. Okay? R, nominal, is the given interest rate, the interest rate that's stated in the problem. So let's look at a few examples. 12% compounded annually, throwing it in the formula, it's 12%. Makes sense. 12% compounded semi-annually, so M is 2, is actually a 12.36% annual interest rate. 12% compounded daily is a little tricky because the exponent is 365 and the denominator here is 360. And we get an interest rate of 12.935%. You'll notice a homework here. Don't want you to skip the homework. Now, the next slide I definitely like you to pause and do all 5 of these. 8% compounded annually, 7.75 semi-annually, 7.79 monthly, 7.7 daily, banker's rule, and 7.7 compounded daily, exact time, exact interest. Okay? I want you to calculate these and observe the different annual interest rate and tell me which is the highest interest rate. This last one we very, very rarely use, so don't worry about memorizing it. So please pause the video and do those. Okay, you're back. Compound interest partial payment. Well, up until this point in compound interest, it's really been let me go back here. Up until this point, it's been a perfect world here, compound interest. We took money out on the first of the year and took it out on the 31st of the next year for exactly 1 year. Or if it's monthly, we took it out on November 1st and then took the money out on July 1st. We know that's not really what happens in life. You might put it on in the account on July 2nd and take it out on December 8th. And it's compounded monthly. So how do banks handle that? Well, on question 13, we have partial payments. Oh, I'm sorry. We're first going to discuss partial payments, meaning in the middle of a period in a term, we are going to withdraw money. So you'll have $2,000 in an account paying 5% compounded semi-annually for 5 years. At the end of 2.5 years, you withdraw $1,000. How much will still be in the account? Determine how much will be in the account after 2.5 years. Okay, please pause this and write a timeline. So let's look at this problem. Number 13. We're going to draw a timeline. You have $2,000, 5 years. At the end of 2.5 years, you're going to withdraw $1,000. So this is compounded semi-annually. You're going to find the future value of the $2,000. So the future value of the 2,000 is right here. Again, first find n, which is 5, and I, which is 0.025. The future value of 2,000 after 2.5 years is 2,262.82. You withdraw 1,000. That leaves you 1,262.82. And now you find the future value of that amount at 5 years again. And you have to recalculate N and I. So when you do that, your future value of the 1,262.82 is now 1,428.76. Okay? Now, what happens this is what I was talking about a minute ago. What happens if you withdraw before the full period? So number 14. Okay? So a person invests $9,500, 7.5% compounded quarterly on September 1st, 2000. What is the value of the fund on July 15, 2004? Use banker's rule, simple interest for part of the period. So the most difficult part is finding N. So here we are on September 1st, okay? We're going to withdraw it on July 15th, 04. But we have to calculate full quarters as close as we can to July 15th without going over. So first go year to year, 9/1/2000 to 9/1/2003. So there's 3 years here times 4 quarters, or 12 total quarters. Now we're going to count quarters from 9/1 to December 1 is 1 quarter. December 1 to March 1 is another quarter. March 1 to June 1 is a third quarter. So there's 3 quarters here. Now, before we go over and withdraw it, we have to calculate with our compound interest formula a total of 15 quarters. I is 0.075 divided by 4. We find the future value of $9,500 on June 1st is $12,552.72. I recommend you pause this to verify all these calculations. So on June 1st, we have $12,552.72. Now we have a part of a quarter. And what do we do for part of a quarter? We use the simple interest formula. So from June 1st, 04, which is day 152, to July 15th, 04, 196, there are 44 days, and we use this simple interest formula. Oh. Simple interest formula. And so on July 15th, the value of our investment is $12,667.79. So we use compound interest for full periods and simple interest for partial periods. Now we're going to do the reverse in question 15. Non-interest bearing note is $24,890. I gave you the future value, right? Non-interest bearing means I gave you the future value. So we have this note we're holding on to. We're coming along, and it matures on March 1st. But on October 6, 2003, we want our money back. So we want to find full, this is compounded monthly, so we're going to come back and determine the number of periods, the number of months between March 1st and 09 and 11/1/03. So I want you to pause it, see if you can calculate the total number of full months. I is 8% divided by 12. And then, once you get full months here, this is part of a month. This is the same problem. Right here is your timeline. So we find our future value. We're first going to find our proceeds right here in 11/1/03 with our compound interest formula. I should say it's our proceeds formula for compound interest. You'll notice there's a negative exponent. You can put that in the denominator if you want. So I want you to pause this, find our proceeds right here. That amount should be $16,286.25. By the way, the number of full months you should have calculated was 64. And then now from November 1st, 1 to October 603, there are less than 1 month, so we have to calculate the days. So the days are 26. 305 minus 279, and there should be 26 days. We're going to use a simple interest discount, use the simple interest formula, and then to find the discount amount is the future value minus the present value. So we have a few homework problems here. Page 77, there's 17, page 74, 35. And then on Blackboard, there's practice on your homework sheet called partial payments, 1 through 5, with the answers. So try those. Okay? A note with a maturity value, excuse me, $15,000 is due in 5 years, 2 months. If interest is given for part of a period, what is the present value of 7.5% compounded annually? Again, this is the same thing. We're finding the proceeds. I made it a little bit easier. 5 years, 2 months. So you go back 5 years and then you go back 2 months. I'm going to stop here and let you calculate this. And this will conclude the first unit on compound interest. This concludes the first unit on compound interest. We're going to, my next video will be on compound interest, and we're going to do some things that we did in simple interest, like find 2 equal payments. We will find which deals are better, getting money now or getting money in the future. So you can stop the video now, and we will print out the next handout for the next video. Thank you.